Thanks for the opportunity. So I'll be. It's a privilege opportunity to present in front of you, and I will share about some of the works that we have been doing for the burn injuries and burn patients using the deep learning. And so I am a faculty member in the Department of Computer Science and Engineering here at IIT Ropert, and I'm also serving as an associate faculty with the Department for Biomedical Engineering here. So I'm just making it the full screen. So I will be going through the problem motivation and the introduction, following that with the dataset description and the other categories of the problems that we have catered to, the burn images body part classification, why that is important, and burn severity estimation and the burn region segmentation. Then some another work which is not related to the deep learning based, but it is for the particular problem of the burns. So we call our project, this project that we are doing, it's self-motivated project. It's we call this project as burns. We want to reduce the number of burn injuries and get the people treated as soon as possible. So that's why we named the project as the burns. So the motivation. So burns is a very serious injury affecting large number of people, and even as per WHO, 180,000 people just lose their life, and many more become crippled forever. And you know that the suffering that they experience while living is going to be really torturous for them. And is this a problem for countries like India or developing countries? Not exactly. Even in UK, USA, there are large number of burn-related deaths every year. So of course, in our country where we also there is a lot of people there, the number of people per unit of area is very high. The density is very high, population density is high, and we use a lot of the oils and other kinds of things, which makes it also make the people more prone to the burn injuries. So number of injuries are quite large. So before proceeding further, let me tell you briefly about the skin anatomy. So there are three layers of the skin: epidermis, dermis, and hypodermis. So accordingly, the burns that affect, they may affect the different level of layers. And if they affect the innermost layer, the hypodermis layer, then it becomes a very severe burn. And burns is a special category of wounds. So it requires a special different treatment in terms of the treatment, also in terms of the deep learning applications also. So that's why we have just highlighted here that there are different kinds of wounds. Within the wounds also, we are just focusing on the burn injuries here. So these are some different causes of burns. So thermal burns, which we mostly encounter. And the thermal burns is a serious number in terms of the total number of burn injuries because of fire, because of hot liquids and something like that. Then there are sometimes friction burns, chemical burns, electrical burns, and the radiation burns as well. The number of cases for the radiation burns and the chemical burns are generally less, but there are sometimes like people who construct roads, they go through the chemical burns and something like that. The sportsmen and other people sometimes go through the friction burns. And of course, the electrical related people, they face the electrical burns also because of shock and other treatments and so on. In terms of burn severity or the burn degree, there are three different types of burn severity. We label them first degree, second degree, third degree, and we can also give them the severity: low burn, moderate burn, and severe burn. As such, severity is a function of both the area, how much is the area of the burn body is burned, and how much is what is the degree of the burn. And now coming into the issue. So burns treatment, burn diagnosis require one to identify also the total burn body surface area as well, which we call TBSA. And for that particular thing, we need to perform the burn segmentation as well. And secondly, burn segmentation is also important for the degree classification. What is burn segmentation? Burn segmentation is basically given a total image of a particular person, including one skin and the area of the wounded region where the burn injury is occurring. We want to identify that region only, as you see here, which is actually burnt, only that portion. We want to identify how much this pixel, this area is contributing. Okay. So, and secondly, if we want to classify the different level of burns in different categories, whether one is low burn, moderate burn, or severe burn, then also it is presumed that the segmentation can help improve the quality of the burn severity and burn degree estimation methods also. So that brings us the need for the burn segmentation methods. So this is the current method that has been followed by the doctors in estimating the total body surface area which is burnt. So earlier, the long time back, the Palmer method used to be used, that 1% of your palm is basically, if the body of the person that is burnt is this much covered, there is 1%. So accordingly, we will compute. If you see in this slide here, that there is a map that the doctors are using in PGI here nearby, and it is a similar thing that is used in a lot of burns hospital. So the doctors will mark the markings and estimate that how much area of the person of the body is burnt, because the treatment require giving the fluid to the patient, and then the how much fluid to be given to the patient is dependent upon the total body surface area. So that's why we need to know how much the body surface area is burnt. There is a total fluid requirement formula, Parkland formula, which given an input to the TBSA is given as an input. It gives you the values how much the fluid requirement for the person is. But in order to estimate TBSA, the current methods that are used, they are very, very traditional methods. It's just hypothetical methods. There is not much progress. These are very old methods. If you see from 2004 onwards, these are the methods. The best method that has been used, which is considered nowadays the benchmark, is a London Browder chart, which the doctors use. So there the body parts have different portions of the surface area percentage. So if your chest is one little bit, they count it as a 13%. Some doctors customize it by themselves, but more or less Lund Browder chart is a driving force for them. So there is no clear, accurate model that given a body person patient image automatically can compute the burn surface area percentage. Even we are in the progress of that work, it is still a big challenge. So as I mentioned to you already, the reason for working on this burns problem and what are the different types of burns and what are the stages of the burn diagnosis involved. So now what is our motivation? There has been a work earlier recognizing the burn degrees and burn other aspects of the burn injuries using the color images. But that was a time when the machine learning and deep learning technologies were not advanced. Also at earlier time, not the good quality camera images were available. So earlier the laser Doppler imaging based modalities were considered good, but that have another challenge. Laser Doppler imaging infrastructure is very, very heavy. It's not easily portable. It's very highly costly. So even in USA, many hospitals cannot afford to have the LDI based imaging modality to classify the burns objectively. It's just subjective assessment. Doctors make a visual perception about it and they make some estimation and give you the treatment and so on. But as we understand that the subjective treatments have their own accuracy issues, so it is reported that only those subjective estimates are only 50 to 70% accurate. But now, given the advancement in the technology, in terms of the camera models that are available to the people in very easily, every phone has nowadays very good camera models within them embedded. And secondly, a lot of recent progress in the machine learning and data sciences, as this conference is all about. So we wanted to also explore that how these deep learning approaches can be efficiently utilized for this model, for this particular problem. So that was our motivation to explore. So there are some objectives that we identified in our problem. So I will now just briefly describe the data set of our problem, and that is a specific case for every other problems as well. That we prepared a data set from we have some collaboration with the doctors, but the complete IRB approvals is yet to be taken. We got duly supported with one of the expert surgeon who had more than 30 years of experience, and he has been working as a ex-HOD also in the Safdarjung Burns Hospital. So that really helped us a lot in this particular work. And we collected our data set of images because of the ethical issues and other issues. We did not want to delay the work. We collected from the internet manually and then segmented it in consultation with the doctors and categorize our data. So we have a large scale of data, which is around 604 images through the internet collections. And we gave them the different body parts also we identified. I will tell you why we came to the body parts. But the problem that we want to solve is that what is a burn degree, or you can say burn severity. And secondly, identifying the burn segmentation so that we can make automated burn diagnosis models. So these are the different body part classes, and these are realistic data. as these images are collected from internet, so they have the different illumination condition and everything. So the burn images body part classification. So we wanted to just prepare a model which will help us identify whether it is a hand body part or other face body part or inner forearm or back, because these are the 4 body part areas that are most prone to the burn injuries. Why we are doing it? First of all, body part classification, because that is nothing to do with the burn diagnosis. The reason is our hypothesis that we explored, and we will show that we want to develop the efficient methods for burn images, body part burn images classification. The reason we identify that in general, the body skin properties are different at different body parts. We all know our skin property at the face, at the chin, at the chest part, the stomach part, and other body parts is different. It's not exactly same, right? So the skin characteristics, the depth of the skin quality is completely different body parts. So different burn injuries reflect differently at different body parts. So their characteristics, the output when we capture through the color image or something like that, that will be slightly different for the different body parts, even though their severity level may be similar. Second thing is this, that when we are giving these deep learning models the images, okay, for a particular anything for classification, they also, if they are not customized, if they are not made specific to the different body parts, then try to understand that we have a limited data set. We don't have a tens of thousands of images or tens of thousands of data with us. So the challenge that it becomes is that the model has to generalize against the body part and able to make the prediction for the burn degree classification or the segmentation, which is very difficult in general. So the hand image is completely different looking compared to the face looking image or the chest looking image, and so on. If similarly, the hand with the fingers is very differently looking. So instead of generalizing a particular model that performs the burn degree classification, despite having the images of different types, we wanted to develop a burn images body part classification first, and accordingly perform the segmentation models. Accordingly have the segmentation models. Okay. So for this particular reason, we understood that we want to go for the customized deep learning models. Customized deep learning models is body part specific models. So our first task would be that given a burn image, make a automated classification for the burn. So we tried the existing simple deep learning models. There are very good literature in that particular sense. ResNet, VGG16, VGG19. These are the standard benchmark deep learning models for the classification that has been used. So we also tried that. So there we proposed another approach also. Now these already trained models, they have been trained on a different kind of a data set, all world images. So they do not again generalize for the body part problem. So, and our data set of the burn images was limited, even though we have a good number of 600 images, but still it is generally less compared to the number of images required for a deep learning model at times. So we enhance the improvement in our model using the known burn images. We took the known burn images and collected from the computer vision different problems. Known burn images data sets were available. We use that to train our model for body part classification. Then we fine tune our model. Deep learning models are fine tuned later for the burn images only. And we will see that what the accuracy of these models are. So these are some images, and burn images and the known burn images. So this is just the simple description of our data set, that how much images we have in the data set. Earlier, then we were performing the burn images body part classification. That time we had only very limited data set, only 150 images only in total, and we therefore enrich our data set using the known burn images. So first, in our final approved model, we will train our model using the known burn images and then fine tune it using the burn images, as you can see from this particular architecture. And the base model could be any standard architecture that we can consider about ResNet, VG16, VG19, and so on. And then we perform the classification using softmax and so. So we also compared this accuracy with the standard machine learning models. Compared to the machine learning models, we find that the ResNet 50 based BI-BPC method was performing better. If we are just thinking about BI-BPC right now, and this is the class-wise accuracy for the different deep learning models, ResNet 50, VG16, VG19. Class-wise accuracy-wise, for some classes VG16 performed better, and for some classes the ResNet 50 based model performed better. But consistently, this is observed that deep learning models, despite these are the pre-trained, these are the fine-tuning, or you can say the transfer learning approach that we are using. So transfer learning approach along with the deep learning in that sense is better than the machine learning approaches straight away. And we further improvise the accuracy up to 90% using the additional data set of non-burn images. So please, I want to give you all also the insight. Many times a realistic problem in biology or any other area that you would be working, the deep learning, the data sciences are very much crippled by the fact of the limited data set. So in any case, sometimes in your problem, the data set is limited, but we also highlight from our example also, if you can enrich your model performance by using some similar data set of other domain, that also can help the improving the performance of your method. And we can see here also, so using the non-burn images improved the accuracy by almost 10% overall. So this is the class-wise accuracy of these models. For some particular cases, we did the almost a threefold validation. So for the 3 different folds, we got this kind of accuracy. Now coming to the main problem part 1, which is burn severity assessment. So referring to the literature in a particular domain, this particular domain, there has been very limited work in exploring the deep learning approaches or machine learning approaches which are burn images based. As I told you, the visual images based modality considered in the burn images, but it has not been that successful. So there has been very limited work in this particular domain, unfortunately. So earlier images were using just standard image processing based methods and using some psychophysical experiments with the consultation with the doctors and making some multidimensional scanning analysis, but they were tested again on very small limited data set. If you see, all these initial works were tested on around 100 images only, and in this particular work they have tested, but they also used very standard simple models only and applied SVM and simple CNN ResNet only. And then recently there was another work, but they tested using only 23 burn images only, very limited data set again. So compared to these literatures, the performance that our models have performed is quite a bit. Our data set, it's not an exact formal comparison because different approaches are not easy to implement and repeat because they were psychophysical experiment based. But overall, if you see here, the data set, the number of the images in the different data set that has been considered and the accuracy values are being reported here. Now let me tell you the model approach that we are taking. As I mentioned, we are taking a 2-stage approach. First, we are performing the burn images body part classification. Then the second approach is burn severity estimation, or we can say burn severity assessment model. So first body part classification, then the customized deep learning model will be activated on that particular image to make a prediction. So given this hand image, so body part classification network predicted fortunately correctly that it is the hand. So accordingly, then the next time the burn severity assessment model of the hand only got activated, and that worked on this particular image and predicted that it is a moderate one. And this is also rightly the case. So again, we use the transfer learning approach only here. We have the pre-trained network which we used and then fine-tuned it using the deep learning. But what we did was we did not just use the complete end-to-end the softmax layer. We used the feature extraction extracted through the deep learning model, but applied SVM after that. We found that the results of the SVM compared to the softmax were better. So that's what we are doing it here in this particular. But the features were not handcrafted features. Features were coming through the deep learning model. So that was a slight difference. So first perform the body part classification here. The overall architecture is this. First perform the body part classification. After you get the classified image, then you feed it into the base model, which could be ResNet 50, VG16, VG19. Let us see how their performance is. And then that the output is 1000 crores because we are taking the pre-final layer output. So 1000 cross one size feature, and that feature vector has been then tuned to the, that been provided to the SVM classifier for the final prediction out of the severity, whether it is a low severe burn, mid moderate severe burn, or the severe burn. Just a minute. Okay, so this is a data set description of these particular experiments that we have performed. So we also compared these our customized BSAM. They are going to have the less number of images within the model itself. But the generic BSAM, although it is generic, but it has a leverage that is having a larger data set. So we also compare and present the results that even if a deep learning model which has been trained with a large number of images compared to the customized models which were trained using the less number of images, how does the performance compare for these particular models? So what we observe from this here, that the generic model we found, we can I think summarize the results here better. Okay, so the generic models was not performing that good compared to the body part specific models, and within the body part specific models also, if you consistently observe that the ResNet 50 baby BSM ResNet 50 has been performing really the best consistently. If we can observe that the blue curves are here better for different metrics, either we take the accuracy, F1 measure, or the recall. We also prepared another data set that we collected later using, we purchased some images from the iStock, that's a website. From there we purchased some images. It costed quite a bit of amount of money, but finally we procured some images and tested the performance of our model against this additional set of images. And there also we consistently observed that the BP BSAM model with ResNet 50 is consistently performing the best given the different measures. So this is the overall approach again highlighted here, and we compare that the performance is comparatively better compared to the actual image. So these are the few examples that has been mentioned here, and these are comparatively results compared with the existing image processing based handcrafted feature based approaches applied with SVM. So ours compared to the standard image processing modalities, those Herlich features or local binary pattern or histogram or gradient, they are some of the feature extraction methods for the known to the image processing community. Compared to that, our model is around 20% better, which is deep learning based. The features are extracted using the deep learning, and the model accuracy was comparatively overall much better consistently on the different data sets. Here the results are on UBA data set. So these are the overall results that we are mentioning. So this work led to some publication. I am thankful for my PhD scholars who have contributed. Particularly Juhi has been leading this work, and the surgeon from the Southern Burns Hospital who has been assisting us a lot. So this led to some good publication in this particular domain. Then coming to the challenging the problem, the last part of this our talk, the segmentation. So as I told you, why we perform the segmentation, because it is important for the burn severity assessment and also for the primarily TBSA estimation. In TBSA estimation, we have to have the burn segmentation. We want to know how much area of the body is burned. So we want to develop the automated models for the TBSA estimation. So that's why it will require that just click an image. Can we compute the TBSA? So that will require first task is segmentation. And in medical imaging, the image segmentation is a very rich studied problem, but most of those works have been done on CT images or X-ray images and so on, so they cannot be directly used here. We have to think about the good segmentation approaches which have been used in the color images domain. So these are some existing methods that has been explored for the segmentation, and again we find the similar limitation that earlier works have been really old and their accuracy is also limited. They tested on a very limited data set. Only recently some work have tested on the larger data set, and they propose very basic segmentation network model, SegNet, which is a very known 2017 work. SegNet, the latest work in this particular domain in the burn community reports the SegNet to be the best performing model. And these are the models which have been used in the color imaging community and the computer vision community. You can say that they are considered different. So if you can see, this segment is very highly cited work, around more than 5,000 citations. But along with that, recently a lot of our progress have been made, which we wanted to explore and examine that how effective they are for the burn imaging problem that we are studying. How this problem, burn images, can be addressed using the computer vision knowledge. So we compared and explored these different models. So I'm just mentioning these different models, and they are really published in a very top conference in publication. That's why this ACCV CVPR we are mentioning here. By the very number, the number of papers citing it, that tells that these are quite known and popular methods. Before proceeding further, I think I have to make some assumption here with the audience that they are familiar with the convolution. Okay, so because this concept, if you're not familiar with the convolution, you can ignore this. But in general, if you were to work in the deep learning or applied data sciences, particularly deep learning methods in your domain, then I suggest that everyone have to have the good understanding of the convolutions, because that is the vital step in the any deep learning model. Now, based on the simple, against the simple convolutions, the model that we tried was the Arcturus convolution base. What is Arcturus convolution? We gave it here some neighborhood gap. So here, if we have the consider that we have a here the Arcturus rate is something, let's say 1. So in that particular, Arcturus rate is let's say 6 or something. It can be varying. So here, if we see Arcturus, the Arcturus rate is 2. In that particular case, what I'm saying is R minus 1 neighbors I'm going to ignore before considering applying the convolution. So this is a 3x3 filter. It is not exactly applied for the 3x3 neighborhood image. Okay, we left the gap of R minus 1 neighbors before considering the another pixel. So if you see the domain, the view, the perception that I am capturing when I'm using the Arcturus rate 2 is actually 5x5. Okay. The window that I'm considering is 5x5 window before making some derivation. So higher the Arcturus rate, larger will be my scope, larger will be my field. So Arcturus convolutions have been reported to be really performing good in many deep learning applications. So we also explored the use of Arcturus convolutions. The deep learning based method, the deep lab, which is from the Google, if you see here, this from the Google deep learning lab based method, they're also based on Arcturus. They have considered the 6, 12, 18, but we consider the higher Arcturus rates as well in our model, and we found it to be performing really better. So this is the description of our model. Okay, so there are some technical details here, which for some of the audience maybe right now not that obvious, but it's okay. More the people get familiarized with these terms and the approaches, more it will be supportive in their professional career. That's why I will just go over a bit for this particular architecture. So again, as I mentioned, given the input image, I'm going to consider the standard pre-trained based model, which is having the multiple stages. So I will be combining the features that are obtained after stage 1 and 2, because what my assumption is that for the image, not the high level features only makes a difference, but the low level and mid level features also makes a difference. So I'm considering also the low level and mid level features, and I'm combining them, applying the convolution 1 cross 1 convolution finally to get particular feature map. Along with it, I am also combining and fusing the final output of these features along with the stage 3 output, applying the Arcturus rate at different things. As I mentioned, Arcturus convolution, applying the Arcturus convolution different rates, 6, 12, 18, and 24. And whatever the feature output I'm going to get, I'm going to also merge them, combine them together and make the another feature map, which is out2. And finally, I concatenate both the feature maps, out1 and out2, because that's how I'm going to get the high level semantic features also. And also I will be giving importance to the mid level and the low level features, which are important for my details. I combined them and applied some simple convolutional filters followed with the ReLU activation function, and then finally upsample it to perform my output prediction, which is my segmented output, whether the pixel is burnt or that particular pixel is of burn image, or that particular pixel is not a burn image body part. There is another method that we considered, which is not based on Arcturus as such, but which is combining the spatial stream network and the contextual stream network, the low level features and the high level features, in a different manner. So here we have a simple convolutional network which is going to give me the special features, and again I am using the ResNet 101 backbone network as a backbone network and getting the weights of that particular different stages, out 1 and out 2, and then after some upsampling to get them the merge them together, followed with the fusion of this particular feature map out obtained through this with the feature map obtained through this. And then finally I have to of course apply the upsampling. Here I'm using the global averaging pooling in this particular way, and here I am using the finally the sigmoid function before I finally make the concatenation followed with the upsampling. Here you see the upsampling rate is very high, so I have to because I am getting the 512 cross 512 image, and I have the features which are been reduced to 64 cross 64. I have to apply the high level upsampling in order to get the output prediction. So what we observed here is these are some mathematical aspects that we are considering the two losses, spatial loss and contextual loss. We are combining them together, and this is the description about the experimental result, that what kind of network data set we have considered in our experimental network. And these are the output ground truth data that we generated, again thankfully with the support from the surgeon. And these are some evaluation metrics based on which I will be presenting my results. So again, we observed that for our method, both method 1 and method 2 outperformed the standard state-of-the-art computer vision methods which are there for the color images. Most of these methods have been tried and tested for the other data sets. We will show the results for other data sets also, how we performed compared to that. But we found for the burn images data sets, certainly our performance was very huge, like almost 5% accuracy improvement you can observe here, and almost the segmentation approaches are more evaluated using the Jaccard index and mean, that is mean IOU also. So in that also we found a 70 to 12% improvement compared to the next best state of the art method. So both the methods that we explored, of course method 2 outperformed method 1, but both the methods outperformed the standard known methods. And these are some qualitative results. You can observe here, given this input image, our method is able to make the prediction that this is a burn area. The other methods were having a high recall because they were considering a lot of false positive area as well also in their assessment. Consistently you can observe these images are of different quality and very complicated nature, but our method consistently performed better in predictions. Of course there are some tough cases, like this particular image is a very tough case, so our accuracy is still limited to 85%, 86%, but again in general our accuracy was around 90% or much more than the 90% in terms of the Matthews correlation coefficient, which is one of the good benchmark assessment for binary classification problems. So these are some difficult cases. We can see here, this is very difficult case, the original ground truth we are not able to much replicate, so there is some issue. This is the false positive coming, but you can understand this image illumination condition, the wrinkles here and wrinkles here, and the illumination conditions makes it very difficult. Secondly, again as I told you, face body part is very challenging, and the accuracy in the face body part is very limited for all the methods. The performance of other methods was even worse, it was less than 50%. Compared to that, our models was brighter, but still it is not that good, I would say. So in order to validate our model accuracy, we have also explored performed some ablation study, and we found that all the networks and different modalities are very much important. If we just choose a special stream network, our accuracy is limited to just 64% compared to 75.8% of the final network of the Burns net. If we just consider just stage 4 or stage 3 and stage 4 only, still our accuracy is not that good. It is 72% at best. But if we combine the spatial stream network and also the multiple features that we are deriving from the base method, the multiple stages of the base method, both stage 3 and stage 4, then we are getting the better accuracy, as I shown you here. That here we are combining two stages. Here the stage 3 also and stage 4 also. Both the stages network is combined, stage 3 and stage 4 with the spatial stream network. The fusion has been done here, final fusion. Then that's why we are getting the best network performance. and it is to tell you the ablation study that all these different networks played an important role in coming out with some better results. So we also compared it with the standard computer vision segmentation data sets. So we tried this performance of the model on the standard computer vision data set that we considered. Again, we found the performance of our model is better. So you can see here these. So as you have been hearing about autonomous cars and so on, so that has been the driving force of the computer vision to perform the segmentation there. So mostly it's the scene images that they have performed. Okay. Now, why this this is important. Okay. So I have to compute the total body surface area, which is the one wounded area divided by total body surface area. And I have no clue given the image of the person that what will be the total body surface area of the person. So this work we have been starting doing in collaboration with the National University of Singapore. There has been our collaborator there. So we are exploring there that how we can find the completely automation task for this particular work. So it's quite a lot of stages are there in this particular work, because see, different people can take the images from different scale. So sometimes the image may have large number of your hand body part, but it's not necessary that that is your 100% of the image. So we have to have the scale estimation performed. And secondly, the lateral view, the 2D images do not consider the lateral views. So we have to prepare some automated app which we can, like, move around the body, the burn patient, so that we can get the better accuracy. So we are trying certain models with that particular approach. And now for the so the our model, the burn segmentation model, is thereby here going to make some contribution in finally getting the numerator term. For the denominator term, the total body surface area, there is a famous 3D scanner, and there is a very high quality 3D scanner in NUS with some particular industry where we got some good collaboration. So our task is, again, when the burn patient is going to come to a hospital, we understand that we may not have that 3D scanner with us. Okay, and these are not easily deployable also. Hardly there are any 3D body scanners, complete 3D body scanners in India. So what the approach that we are using is, again, we are using some data science approach of regression basically. So we will be giving the input to the model as the person's face image, person's information, height, weight, palm image, gender, age, and for the limited data set we prepare the complete model using the 3D modeling. And then the regression model for any particular patient will help us estimate the total body surface area as much as accurate we can. So that's what I would stop here. I think even there are a lot of applications as well. I will not go in the interest of the time. We have made some progress in the application as well also. So I will really like to thank the Juhi, who has been in the forefront in this particular, driving this project forefront. And as I mentioned, my surgeon collaborator from the Southern Burns Hospital and my departments for providing necessary resources.